All right, so today in Algebra 2, we're going to finish off Section 3.1, Graphing Polynomials. So I'm going to pick up today in the notes with sketching the graph from a verbal description. So your steps in order to do this, you want to identify or estimate your x-intercept. These will be where your graph changes from positive to negative. Okay, so this where your graph changes from positive to negative. Because remember that where your graph is positive, that means that the graph is above the x-axis. If the graph is negative, the graph is below the x-axis, so it has to cross through the x-axis to change. Okay? You will identify or estimate turning points. Remember that the possible number of turning points is your highest degree n minus 1. And then determine end behavior, and that's determined by your degree and your leading coefficient, and then we will graph it. Okay. All right, so number one, what they tell us, f of x is positive on the intervals negative infinity to negative 4 and negative 1 to 4. So here we know that we are above the x-axis. F of x is negative on the intervals negative 4 to negative 1 and 4 to infinity. So here we know we are below the x-axis. And we also know that we are changing signs here. So these are zeros. Okay. F of x is decreasing on the intervals negative infinity to negative 2.7 and 2 to infinity. And f of x is increasing on the interval negative 2.67 to 2. Okay, so it's going from decreasing, increasing, increasing to decreasing. So we know that it's got 2 turning points there. So we know that gives us 2 turning points. Okay. So our x-intercepts, we have negative 4, negative 1, positive 4. So negative 4, negative 1, positive 4. These are the zeros with the x-intercepts. Okay. So if I come over to my graph, negative 4, x-intercept, negative 1, x-intercept, positive 4, x-intercepts. Okay. Know that between negative infinity and negative 4, so out here, it's above the x-axis. And I know that it is decreasing from negative infinity to negative 2.67. Okay? So somewhere negative 2.67, somewhere around here, down below the x-axis, because I know from negative 4 to negative 1, we're below the x-axis, it's negative. And then from 4 to infinity, I know below the x-axis. Here I know above the x-axis, okay? And increasing, decreasing from that point to this point. And then it says it increases. And then it starts decreasing again at 2, so somewhere up here at 2 is where we are decreasing again. So this is a rough sketch of what our graph would look like. We have 1, 2 turning points. We have our zeros. Okay? We don't need any kind of a scale on the y-axis. No scale on the y-axis. I only know the general behavior. So we only know the general behavior of the graph. So these are called rough sketches. These are not exact sketches. These are rough sketches. Right? All right, let's look at the next one. F of x is negative on the intervals of negative infinity, negative 2, negative 1, 1, and 2 to infinity. So this means it's below the x-axis here. F of x is positive on the intervals negative 2 to negative 1 and 1 to 2. So I know here we are above the x-axis. decreasing from -1.5 to 0 and 1.5 to 0, or sorry, 1.5 to infinity, increasing from -infinity to -1.5 and 0 to 1.5. So let's see, I'm decreasing, okay. From here to here I'm increasing, then I go decreasing, so I have a turning point, and then increasing, turn point, decrease, turning point. So we've got 3 turns here on the graph. So now let's look at x-intercepts or zeros. So we've got -2, -1, 1, and 2. Again, we get that from where it changes from positive to negative. Okay? So I'm going to mark these. So -2, -1, 1, and 2. We know that it is increasing, that it is increasing, not what I wanted to do, thank you. Increasing from -infinity to -1.5, okay? So from -infinity to -1.5, it's increasing. And so we're coming -1.5 somewhere around here. I know that it's negative between -infinity and -2, so something like this. -2, okay, it becomes positive, so it comes up here. It's increasing up into -1.5, and then at 1.5 to 0, okay, it is decreasing. I know that it has to cross through this point, so I'm decreasing somewhere. I don't know how low it goes again. And then somewhere at this point it turns and it goes back up. 1.5, okay? So now I am at positive 1.5. We're going to be increasing. So up to 1.5, and then starts decreasing again. So my graph is going to look something like that. Again, this is simply a rough sketch, not anything definitive. Okay? But we see that we are below the x-axis on all of the intervals it told me. We're above the x-axis on the intervals it told me. We're decreasing and increasing, and we have those 3 turns. All right, so now let's look at some word problems. Interpreting a polynomial model. It tells us in science class, Briley mixes a fixed amount of baking soda with vinegar in a bottle capped by a balloon. She records the amount of time it takes the gases produced by the reaction to inflate the balloon. From her data, Briley created a function to model the situation. For x quarter cups of vinegar, it takes f of x equals -0.12 x cubed plus x squared minus 3.38x plus 13.6 seconds to inflate the balloon. How long will it take to inflate the balloon with 5 quarter cups of vinegar? Okay, so we want to know when x is 5. When x is 5, what is f of x? Okay. We could plug 5 in here, or we can use a graphing calculator. These are nice to use our graphing calculator. We can go to the table function or the trace feature. Okay, so use the graphing calculator. We're going to enter the equation in. So enter y equals in, and then we're going to go to the table. And when x equals 5, it tells me that y is approximately 6.7. So what that means is that it takes approximately 6.7 seconds for the balloon to inflate if we use 5 quarter cups of vinegar. So then it says, part B, what do the x and y intercepts of the graph mean in this context? And do those values make sense? Okay. So again, we're going to look at the graph on the graphing calculator that we have graphed. We're going to find our x and our y intercepts. So my x-intercept, if you look at the graph on the graphing calculator, is approximately 6.6. A y-intercept, we can get that from our graph because it's just my c value, right? 13.6, or sorry, for my equation, 13.6. And so what do these mean? The x-intercept, remember the x is how many quarter cups they're using. And so this says 6.6 quarter cups or cups of vinegar are used. The balloon inflates at 0 seconds because my y is 0. The y-intercept, okay, so my x is 0, so it means if 0 cups of vinegar are used, the balloon inflates at 13.6 seconds. And then it says, do those values make sense? So in this problem, not putting, putting 6.6 cups of vinegar in, the balloon inflating in 0 seconds, that doesn't make sense. It can't inflate in no time. And then if I don't put any vinegar in, the balloon just automatically inflates in 13.6 seconds. So no, neither the x or the y-intercepts make sense. Neither x or y-intercepts make sense. And what that means is that, therefore, we would need to limit the domain and range in this model. So we would need to limit the domain and the range in this model. All right, let's look at another one. Owen is engineering a new brand of shoes. For X shoes sold in thousands, a profit of P of X equals negative 3X to the fourth plus 4X cubed minus 2X squared plus 5X plus $10 in tens thousands will be earned. How much will be earned in profit for selling 1,000 shoes? Again, we're going to enter this into our graphing calculator. Go to the table value. And our x equals 1 because remember we said x shoes in thousands and this is 1,000, so x is going to equal 1. We find out that y equals 14. That's going to be in 10,000s. So 4 times 10,000. We would make a profit of $140,000. Okay. So then part B. What do the x and y-intercepts of the graph mean in this context? And do those values make sense? So again, we're going to look at the x-intercepts on the graph. We can use the calculate or the trace function, okay, of the graphing calculator. So calculate, we would ask it for the zeros. The trace function, you would just trace it until you get x equals, the y is equal to 0. So when we do that, we get an x-intercept of approximately negative 0.86, another one at approximately 1.9. I can get my y-intercept from my equation, which is 10. Okay, so what do these mean in context, okay, to this problem? So the x-intercept means, okay, that, or it says, do these values make sense? So the x-intercept, this is how many shoes are sold. Okay, so x-intercepts are the number of shoes sold with no profit earned. A negative 0.86 does not make sense because we can't sell negative shoes, right? You can't sell negative amount of anything. The 1.9. The 1.9 makes sense that the cost will equal the revenue when 1900, right? Because it's times 1,000, 1.9 times 1,000, when 1900 pairs of shoes are sold. So that's kind of our break-even point. The y-intercept here at 10, right? Basically saying that we would have a profit when we haven't sold any shoes. The y-intercept doesn't make sense because, again, we can't have a profit when we haven't sold shoes. Can't have a profit when we haven't sold any shoes. So again, we would have to limit our domain graph in order for the context of the problem to make sense. And that is day 2 of section 3.1, sketching rough graphs from a verbal description and then interpreting what the polynomial model means.